A directed line segment has initial point P and terminal point Q written as a directed line segment PQ with an arrow over the top, has length or magnitude written as PQ with a set of double vertical bars. When you see the double vertical bars, that's magnitude or length of your directed line segment. The initial point P leads to the terminal point Q. The set of all directed line segments that are equivalent to a given directed line segment is a vector in the plane, and it's denoted by a bold V, which for me it's hard to do the bold, so many times you'll see an arrow over the top of that, but that single letter will represent your directed line segment. Our first example, let's show that vector u and vector v are equivalent. They are equivalent if they go in the same direction and have the same length. So let's check out the slopes. The slope of vector u, we're going to use y2 minus y1 over x2 minus x1. So that is 4 minus 2 over 4 minus 1, and that works out to 2/3. That vector rises 2 and runs 3. Vector v, 2 minus 0 over 3 minus 0, has the same slope. The magnitude or length of each vector, let's start with vector u. That one, we have the square root of x2 minus x1 squared plus y2 minus y1 squared. That gives us 3 squared, which is 9, plus 2 squared, which is 4, square root of 13. The magnitude or length of vector v is the square root of 3 minus 0 squared plus 2 minus 0 squared. That gives us 9 plus 4, which is also square root of 13. Because these vectors have the same length and point in the same direction, we call them equivalent. Definition: if vector v is a vector in the plane whose initial point is the origin and whose terminal point is v1, v2, then the component form of that vector v is v1, v2 with chevrons around them. You'll see that it looks like greater than and less than symbols, but to my knowledge those are called chevron. And the coordinates of v1 and v2 are called the components of vector v. In fact, let's look at the example above. If you were to take vector u, pick it up, and change the initial point to the origin, then v is actually the component form of u. Find the component form and length of the vector v that has the initial point p at 3, -7 and terminal point q at -2, 5. So they give us the starting and stopping points, and I did my best to just eyeball where those are located: 3, -7, -2, 5 for P and Q. Make sure you direct the arrow from P to Q. The component form is x2 minus x1, that's -2 minus 3, and the y component, or v2 part of it, is 5 minus -7, which is 12. This point, -5, 12, represents the terminal point of v if the original point from PQ, the initial point P, is relocated at the origin. So basically, component form is taking a vector, picking it up, resetting the initial point at the origin, and maintain the same direction and length. The length of V if you take the component form as negative 5 squared plus 12 squared, that's 169, and then taking the square root of that, which is 13. Definition, let vector u have components u1 and u2, and let vector v have components v1 and v2, and let's let c be some random scalar. You can add two vectors together by adding their like components, so u1 plus v1 and u2 plus v2. That's how you would add the vectors. Any vector can be multiplied by a scalar. You just multiply each component of the vector by the scalar. If you negate a vector, then you take the original vector and take it in the opposite direction. Same length, opposite direction. And then the subtraction of two vectors is like adding a vector to its negative version. So we're going to take vector u and add the negative of vector v. So basically you subtract like parts instead of adding them. Number 1 you add, number 4 you subtract. Let vector v be negative 2, 5, and vector w be 3, 4. If we find half of vector v, which is a scalar, we'll multiply both components of v by half. That's negative 1 plus 5 halves. That is going to be the terminal point of vector v that's exactly half the length of the original vector v. W minus v, 3 minus negative 2, and 4 minus 5, that gives us 5 and negative 1. Vector v plus 2 times vector w, which 2w is a vector in the same direction as 3, 4, but twice as long. Well, if we take vector w and double both numbers, we get 6, 8. So these are very intuitive as far as adding, subtracting, multiplying. Just be careful to match your parts carefully. So vector v plus 2w, negative 2 plus 6 is 4, 5 plus 8 is 13. Theorem, if vector v is a non-zero vector in the plane, then vector u, which is vector v divided by its length or magnitude, has a length of 1 and has the same direction as v. This vector u, after this process, is called a unit vector, and the process of multiplying this out is called normalization. Example, find a unit vector in the direction of vector v. We're going to stay with vector v being negative 2, 5. The unit vector in the same direction, so we've got to have a vector that points in this direction from the origin, but it only has a length of 1. So here's our recipe. The length of vector v is the square root of negative 2 squared plus 5 squared. That comes out to square root of 29, times the original vector v. So that's going to give us negative 2 over square root of 29 and 5 over square root of 29. This vector points in the same direction as v, but it only has a length of 1. So that's why it's called a unit vector. Double check just to be sure. If we find the magnitude of u, we square each component, add them together. That's 4 over 29 plus 25 over 29. Sure enough, that gives us 1, and the square root of 1 is 1. The standard unit vectors in the plane are denoted by I, which is 1, 0, so you'd go 1 unit right of the origin, and vector j with component 0, 1, so that's 1 unit up from the origin. So this points along the positive x-axis, and this points along the positive y-axis. Vector v has components v1 and v2. The first component is paired with I, the second component is paired with j. This is called a linear combination of I and j. Example, let u be the vector with initial point 2, -5 and terminal point -1, 3. So we're going to have, we're going to let vector v be 2i minus j. We're going to write each as a linear combination of I and j. So vector u, we were given initial and terminal points. So we know how to write that in component form. That's going to be x2 minus x1. -1 minus 2 is -3. y2 minus y1, 3 minus -5, that's 8. And once you've got it in component form, or if you see the numbers in a chevron form, first number's paired with I, second number paired with j. W, that is given in a problem. It's random. It's just given as 2 times u minus 3 times v. V's given in V's given as a linear combination of I and j. Part A, we just found u as a linear combination of I and j. So again, 2 times u minus 3 times v. Distribute like you normally would. That's -6i plus 16j. Plus, now you gotta really watch this. If you distribute the minus, it's got to go both times, or you can choose to put a plus sign and then distribute -3 times 2 is -6, and -3 times -1 is +3. Then add the like terms, -12i, 19j. Definition: if vector u is a unit vector and theta is the angle counterclockwise from the positive x-axis to u, then the terminal point of u lies on the unit circle. Unit vector length 1, opening counterclockwise, just like the unit circle. Your x-coordinate is cosine. That makes the I component in standard unit vector form. And in the second number, the y-coordinate is associated with sine theta, just like the unit circle from trig. Generalization. Vector v is the length of vector v times cosine theta sine theta. Example, vector v has a magnitude of 3, or a length of 3, and makes an angle of 30 degrees, or pi/6 radians, with the positive x-axis. We're going to write vector v as a linear combination of I and j. Okay, so from the previous slide, we have the magnitude of v times cosine theta sine theta. The magnitude is 3. The angle given is 30 degrees. If you choose the degrees, make sure your calculator is in degree mode. These come right off the unit circle, so they're not too bad. If your problem in WebAssign asks for radians, be very careful to use radian mode instead of degree mode. Just be careful with that part. All right, so let's get to it. 3 times cosine of 30. Cosine of 30 is square root of 3 over 2 times 3, and that's the I component. 3 times sine 30. Sine 30 is a half, times 3 is 3/2, and that's the j component. If 2 or more forces are acting on an object, the resultant force on the object is the sum of the vector forces. Let's see what that means. Let me pick a color here. Suppose I've got vector u and vector v. So I've got 2 or more forces acting on an object. if I were to pick up V and reset its initial point on the terminal point of U, which I would take that point, reset it here, maintain the same direction and length as V, and then let me pick a different color here. Connect the original starting point to the end. Then what I have here, what we have here is we still have this as vector V. Now I'm going to take off this part so that it's not a distraction. That green arrow right here is called your resultant force, and it is written with a U plus V. So just make sure one vector, the start of it, is placed onto the end of the other, and then connecting the original start to the ultimate finish, that's your resultant force, or the sum of two vectors if you have it. Example, the two tugboats are pushing an ocean liner. Each boat is exerting a force of 400 pounds. What is the resultant force on the ocean liner? Okay, now I'm not very skilled at drawing, so I just labeled boat 1, boat 2 here. One of the boats is pushing with a force against, here's the ocean liner, it's just this square. I put OL to try to represent it. But anyway, boat 2, from the parallel path, the ultimate path that the ocean liner needs to go, force 1 is 20 degrees up. Force 2 from the other tugboat is 20 degrees down. There's an illustration of this in your e-text if you want to look it up. It's section 11.1 in the Larson book. Okay, so force 1 is 400 pounds of force times cosine of 20, sine of 20. Because it is going in this direction. Cosine is your x direction, sine is your y direction, and that's your angle, 20 degrees. Force 2 is pushing this way or downward from the path of the ocean liner. So it's going to be 400 pounds exerted by that other tugboat, cosine of negative 20, and sine of negative 20. And again, because from the quote positive x-axis, that force is down 20 degrees. Okay, so F is the combination of the two forces from the tugboats. So we have 400 cosine 20 plus 400 cosine of negative 20. Again, you can distribute, and we're taking the front numbers from both components. Then we have 400 sine 20 plus 400 sine of negative 20. Well, since sine is an odd function, the negative can come out front. Cosine's an even function, so the angle doesn't matter if it's negative or positive. Right here, that will stay the same. So just be careful. Cosine's even, so a negative angle, you can replace it with a positive. But if sine has a negative angle, you have to pull the negative out because sine is an odd function. Okay, this first component, that is 800 cosine 20. And then the back part, 400 sine 20 minus 400 sine 20 is 0. All right, so let's repeat why this first part's 800. Cosine of 20 degrees, cosine of negative 20, but again, cosine of negative 20 is the same as cosine of positive 20. So that's 800 cosine 20. And then the sines have opposites. so that goes to 0. In your calculator, 800, make sure you're in degree mode. 800 times cosine of 20 degrees is approximately 752 pounds of force exerted on the ocean liner. Reach out by email, phone, if any of this gives you trouble in your homework. Ask in class, and I'll do my best to help you through it, and I will talk to you later. There's going to be more videos coming.